And here we are in the lab again. Welcome to episode 17. So the way it works is we have mainbrain on one side of the SRAM, and we have our I/O board on the other side of the SRAM. So mainbrain can write to every location of the SRAM. But even though the I/O boards can only write to a small section of the memory, SRAM, there will come a time when both of them will try to write to the same memory location at the same time. So whenever that happens, anytime there's a read or a write to the same memory location at the same time, it causes a write contention, or a read-write contention. So when that happens, the SRAM chooses who is going to write and who is going to have to wait. And it does that by issuing a busy signal to the side that has to wait. Now, you can't ignore this, because as soon as it detects the write contention and it determines the side that has to wait, then that side is locked out from a write, from that memory location. You could go ahead and just go off and just write to another memory location and come back to this one. Or you can just wait for the write to complete on the other side of the SRAM and then write your data to it. Now, if you choose to ignore that there's a write contention and you just try to write anyway, the data's not going in there. So your program's going to think the data is in there when it's not. And I think you can understand that that's not a very good thing for a program. So is what we're going to do today is we're going to intentionally create a write contention so that we get a busy signal on our I/O board side. And then we're going to verify it with the scope that we do have a busy signal being created from the write contention. And so we have to create code to do that. And so that's pretty much going to be 30 minutes. So let's get to it. Okay, let's take a look at our busy signal before we start writing to the SRAM, so that we make sure that it's not active right now, just so that we are 100% sure of what we're doing. So let's get the probe going here. All right. So pin 9 on the connector is the busy signal, and I have it marked, so I'm going to count it one more time just to double check. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. And there we go. So it's high. Not doing anything. No pulses, no activity. Just sitting there. Okay. Okay, so we want to set up mainbrain and the I/O board to write to the same memory location at the same time so that we get a busy signal. So let's load up mainbrain first, because it's the easiest, since it already has memory read and write functions already, so it makes it a lot easier. So we'll get mainbrain first. And the main source file. Scroll all the way down through the initialization code until we get to our main program loop. And then the first thing right after our heartbeat, it doesn't really matter where, but we're going to write so I've made a function for reading and writing to memory, and that's what we're going to do later on our I/O board to make it a little bit easier. So we're writing to memory location 0, and we'll write like 96. It doesn't matter what you write to it, but So we'll just put 96 in there. All right, so that should be the only requirement for main brain. It'll just continually write every time it loops in the main program. It will write to memory address 0, well, SRAM address 0, and then we'll set up our IO board to do the same thing, and we should have a write contention. So let's make main brain a set it as a main project, and I already have the PIC kit hooked to it, so we'll just do that, send it. There we go. Okay. And we're done with that for now. So we will close that up and set this back as the main project. And now we'll set up this guy, our IO board. So we're already up here. So we want to take this out here to about right there. So, and this too, and variable A, we don't need that. So just take all this out. Okay. So we're going to write to address 0. So we set our address, and then we got to do it continuously. So it'll be in our main program loop. And so we'll come down here, and we have to do chip enable. And this was the in, so we want to take that. We'll save the busy part. We'll use that. Chip enable 1. All right. So then the first thing we have to do is set our direction to 1. So let's just copy this right here. Do it like this. So we'll enable our SRAM. Then we will set the direction. So my note here says 1 is right. So we'll do a 1, and we don't need to do the triz because you only have to do that one time unless you're going to change it. And so we're going to end. We're going to have an end down here because we want to put it back to a 0 when we're done. All right, and then we'd have to do the read and the write right here. Move it over and take out the triz and 0 for write. And then we want to put it back. Whoops. Do that again. Okay. And then we'll put that back when we're done. So the read, write. Okay, so we're good. So now all we have to do is the actual output of the PMP, which is, we'll go to our data sheet here. And so that one is PMD out 1. All right, equals. And we can write anything to it. We'll write 69. The other one's 96. We'll write 69 just for fun. All right, so then that checks for, it has its own busy signal when it's work doing the process, doing the operation. And so we want to wait until it's done and drag direction. I put that in the wrong place, didn't I? We got to get this thing up here. Right in between these two read and write guys right here. There we go. That looks better. All right, so that should be our read write thing right there. And we're not going to do anything to the port. We don't want to write to the port, so we'll just comment that right now. So the only thing it'll be doing is just writing to the port. And that will definitely cause a write contention, I'm sure. So let's send it to the I/O board and see what we got. Okay. All right, well, let's take a look at our busy signal and see what it looks like now that we're writing from both sides to the same memory location. Okay, so yeah, you can see that for a short amount of time it's inactive, but most of the time it's low. Let me see if I can change that time a little bit. There we go. Yeah, and it's pretty consistent time-wise. All right, so there's our busy signal. And that confirms that we are getting write contentions. Every time that signal is low, then we have a write contention. So that wasn't so bad. So before we started, we checked to make sure the busy signal was high and inactive state and static, not doing anything. And then we wrote to both sides of the SRAM to the same memory location at the same time and generated a busy signal and verified it was a scope. So now we need to generate an interrupt every time that busy signal goes low. So that's the next thing. We'll do that next. We'll configure the interrupt and then we'll verify that we really are getting an interrupt by lighting up an LED when the interrupt occurs. So let's get to it. Okay, so we're going to make a new file for our interrupt code. So we're going to go up here, file, new file, C source. And the file name will be IO board interrupts. All right. And then we'll come over here, copy the header information, make it a little easier. Paste it in our new one, and then we just have to change this. All right. And then we'll save it. And so the first thing we do is we got to initialize our interrupt. So initialize the microcontroller to do interrupts. So we're going to have a function here that returns void IO board interrupts init and void there too because it doesn't take in any variables. All right, so there's our initialization function. And then we just need one more function, and that's our interrupt handler. Okay, so this is the way that they recommend you do it. So this is our actual interrupt routine that's designed, it's defined in the data sheet. So you have to use this name right here. And so then there's some attributes that you add. So the interrupt attribute, so you're adding two attributes. So the interrupt attribute just tells the compiler that you want to, and they're compiler specific too, but it's telling the compiler that it is an interrupt, and then that changes the way that it handles the data, because it has to like push certain data off into the stack and then retrieve it after the interrupt, so that you don't lose certain things about like the program counter and stuff like that. And so then the other attribute is this no auto PSV. So this is since most of the variables like the registers and stuff are in there's a lot of flash memory stuff mixed with RAM stuff. So this just makes it compatible with an interrupt, basically. So basically, this is your basic format for your interrupts. And this is the handler routine defined in the data sheet. So whenever this interrupt, whenever a pin change occurs on port D, then this interrupt is triggered if it's turned on up here. We want to add this to our build list, our list of source files to build when we build the project. So we will come over here and we'll add existing item, IO board interrupts, and that should get us in there. And so then we have to define our prototype in the header file. We don't have to with the interrupt. It's already compiler built-in things here. So, and this is just microchip stuff here. It's not a C, the C language. It is a compiler specific item here. So we want to define our prototype in our header file so we don't get warning, an implicit warning from the compiler. And so then if we compile that, it should all be good. All right. Okay, so port D13 is mapped to our busy signal on the IO port. Okay, so we have to make that an input first. So it's trisd dot 13 equals, and if you remember, an input is a 1 to make it an input. And it's an input because the busy signal is going in to trigger the interrupt. All right, so now it's also can be an analog input, so we have to disable the analog input function. And 13 equals, we have to turn that function off. Whoops. Okay. And so let's put a note up here, get our notes going. So configure port D.13 as an input. All right. And now we have to enable the change notification event. Okay. All right, so enable change notification event. All right. All right, so then I go to our data sheet here. So then that is our control register for D. So we're going to want this guy right here. And we have two. We have to do enable it, and we have to select the style. So it's edge. We want edge to change, detects edge transitions. So we come up here, and then that's a D, then bits dot. See, now this is on. So we have to we have that on issue. So we will do our bitwise OR, and we want it to be a 1, and it is bit 15. Whoops. Okay, whoop, listen up here. All right, so that will turn it on. All right. Now we have to define the edge style, well, the style of our notification to the edge style. All right, so I'm going to copy this for my notes. All right. Okay. So then that's the same thing here. And we'll use the bits on this one. And that's going to be our style, and that equals 1 for our edge, detects edge transitions. And I think I'll just shorten that up a little bit. All right. So then the next thing we have to do is define whether we want to trigger the interrupt on the rising edge or the falling edge. All right. So our busy signal is normally high. So when we get a contention, the busy signal is going to drop low. So we want to go from high to low. So we want to set for falling edge. All right. Trigger. Okay. All right. So there's two registers to control that. There is CN, EN, O, and then we're doing D. And bits. So we're doing 13 equals, I believe, so the CNEN 0 is the falling edge. So we want that. We want to go from high to low, falling. So that is a 1. And then the other one is CNEN1 D bits. And our 13. So that is from the rising edge, from low to high. So we don't want that. You can do both. You can have an interrupt triggered on the falling and the rising edge. All right. But we only want the falling edge. So then this is going to be 0 because we're not going to trigger off of that. All right. Almost there. So the next thing is to set the interrupt priority. And that interrupt priority is 4 by default, but we're going to set it here anyway, and because we might want to change it later. But right now, so we'll just go priority. All right. And then if we come over here to our data sheet, change notice on D right here. So the interrupt priority is IPC 18. All right. Bits. And we want CND, change notification on D. And we want that to be 4, which is default, like I said. All right. So then we have to enable the interrupt in general on port D. Well, actually, it is a change on interrupt. So now we have to do the change on interrupt. We have to enable it for port D. All right. Change notice. Interrupt on port D. All right. So if we look at our data sheet over here again, same place. So the interrupt enable is C4, IEC4. Okay. All right. So bits. Whoop. Yeah, bits dot and change on interrupt right there. I couldn't see it. And we want to enable it, so that's 1. And then we want to clear it. Make sure the flag, the interrupt flag, is cleared when we start, because if it's a 1, then we're not going to see any interrupts. So clear the interrupt flag. All right. So then back to our data sheet. So then that's their flag register right here, IFS4. And put that in there, bits, dot, change on D, interrupt flag equals 0 for that. So last but not least, we have to enable the global interrupt enable, which is for any interrupt to occur, this has to be turned on. And you can use it to turn interrupts on and off across the whole microcontroller. So enable global interrupts. Okay. And that, if we come to our data sheet over here, is Intcon 2, interrupt control register 2. And that's bit 15, the GIE. All right. So come over here. So interrupt con 2 bits dot GIE equals 1. All right. And another one we should just do is interrupt controller 1 and turn off nesting, interrupt nesting. Okay. So now that we have our initialization code, we need to call it from the main function for it to actually initialize. So we're going to put it down here towards the end, just before our main program loop. We're going to put it right after initializing the PMP, because you want to initialize the PMP first, then the interrupts, and we don't have to have the void in there. All right. Okay. And that we'll call it the initialization code. Now the only thing left to do is just to do something when we get an interrupt. So when this interrupt occurs, then we have to clear the flag. So that's the most important thing, is to clear the flag. So if you remember, that register is IFS4. Whoop, 4 bits. Oh, I still didn't get that out of there. And then it's a change notification on D, interrupt flag. And so we have to clear that, set it to 0. So that way another interrupt can occur. All right. So then we have to, that's if any pin occurs. And we only have one pin, so we could get away with doing something in here with that. But later, we're going to have another, at least one more interrupt. So we want to distinguish which pin it is, because once you get the interrupt, then you have to say, okay, a change notice occurred on D, port D, but which pin? So we want to check. So then in order to determine which pin, we have to use the CNFD register over here in our data sheet. So when basically the flag becomes a 1 when an enabled edge event occurs on our port and our pin that we specify. So we're using the CNFD in this case for us register. So CNFD bits dot change notice flag for D13. That's our, all right. So then it's what we want to do is if that occurs, if it's a 1, then we want to do our code, what we want to do. And then when we finish that, we also have to clear this bit back to 0 so that we can get another interrupt. Otherwise, it'll just throw one interrupt and you'll never get another one until this is cleared. All right. Okay. So then we want to do something here. So when we get an interrupt, and just for our test, we're going to turn on LED 7, which is the green LED. And it doesn't like that because we have not included our header file, IO board H, right here. Okay, that will fix that. So now LED 7 will be on, so we should be all set. Let's compile it, make sure we didn't mess up somewhere. All right, and so it likes it. Okay, so let's go. Let's see, we're reading and writing on both, so all we have to do now is to see if there's an interrupt. So we need to send this to IO board and see if it triggers an interrupt and turns on our LED. And it does. That is really cool. And so we did, we got the busy signal going, and then we got an interrupt going. So we have an interrupt. So the next thing to do, and this will be the end of this video. So in the next video, we will define functions for reading and writing to SRAM so that when we do get a busy signal and it creates an interrupt, that we wait for the other side to finish their write, and then we'll finish our write. And then our data should be solid. We should have reliable data, and that's very important. So I'll see you in the next video.